All right, so let's get going. 7-6, solving equations. And these will be exponential equations and logarithmic equations, and using various methods to do that. So we'll start with what I think are the easier ones. And you'll have something like 4 to the x is equal to 2 with an exponent of 3x minus 12. And the kicker with these types of equations is that you've got the variable in the exponent. And when that's happening, you've got to do a couple of different things that are possible. One thing that's possible to do is get the bases the same for each side if you can. Okay, so when I look at that, I think, okay, if I'm looking for a base, then I'm probably looking for a smaller number. Okay, so I look at this one, 2 doesn't break down any, does it? It's a prime number, right? 4, can we write 4 as a 2? It's really what? Think exponentially, not multiplication-wise. It's 2 squared, right? So if 4 is 2 squared, then we really have this equation. What's the exponent property for that? Close. Multiply. Okay. If there's parentheses and the exponent outside, the rule is to multiply those. So this is really 2 to the 2x equals 2 to the 3x minus 12. Once the bases are the same, it's kind of like when we did rational equations back before Thanksgiving. Once the denominator was the same, we didn't have to worry about them anymore. Once the bases are the same, you don't have to worry about them anymore. You drop them, and you get 2x equals 3x minus 12. And solve that equation. You know, good old 7th grade math right there. Subtract 3x. Negative 1x equals negative 12. Divide by negative 1. X is 12. Get the bases the same. And then that allows you to do that. Okay. That will be same idea. 9 to the 2x equals 27 to the x minus 1. So 9 and 27 are the bases right now. What number relates 9 and 27? 3. So we want to try to rewrite those as 3 is the base. Okay, so 9 is actually what? 3 squared. 27 is really 3 cubed. Yeah, 3 to the 3rd power. And then what's the exponent rule here and here? Multiply them. So that's going to be 3 to the 4x. And then that's 3 as the exponent times x minus 1. So that's actually 3 to the 3x minus 3, like distributive property. And now the bases are the same. They go away. And we got a pretty easy equation to solve there. One step. X is negative 3. So the exponentials are exponential. These are exponential equations because the variable's in the exponent. That's what makes them exponential. But not too difficult, but you just got to think about bases and exponents for doing these. Let's do a more difficult one. 81 to the 3 minus x equals 1/3 to the 5x minus 6. This one takes a little more thinking involved because of the 1/3 there. We got to think about what number relates 1/3 and 81. sometimes that's a little tough to think of. So sometimes if you're unsure what number to relate, take the biggest number and just break it down with a factor tree just to see what makes up 81. Well, I know it's 9 and 9, and 9 breaks down into 3 and 3. So 81 is really 3 to the 4th power. So 3 being the base, pretty good chance if 1/3, there's a 3 in it. So how could I write 1/3 is 3 to what power? Think back to some Algebra 1 stuff here. How do we bring that 3 from the denominator up to the top? Negative exponent. That's exactly right. It's really a -1 exponent. That 1/3 and 3 to the -1 power are exactly the same thing. Okay, so this is really 3 to the -1, then 5x minus 6 is the exponent. And then again, what's the property for those exponents? Multiply. It's distributive property on each side. So that's 12 minus 4x -5x plus 6. And I've already dropped the bases because they're the same now. So I'm just dealing with the exponents as my equation. And then just solve whatever way you want to there. I'm going to subtract 6. Hopefully with these equations like this, y'all are to the point in your mathematical careers where you should be able to do more than one step at once. If you can't, that's okay. You can still do it one step at a time like I'm doing here. X would be -6. So you've got to think about the bases that are there and try to manipulate the numbers to make the base the same on each side. The fractions, the ones with the fraction in them, are definitely the hardest ones of that style. So let's do another one with fractions in it, just so that we've seen a different version of that. 32 to the x, 1/16 to the 3x minus 2. What do we know about 32 and 16? 16 is half of 32, which would say, okay, well, I know 2 goes into 32 because 16 and 2 multiply to be that. Does 2 go into 16? Yeah. So I'm thinking maybe 2 is the base. How many 2's are in a 32? 5 of them, right? 4 and 4. So that's really 2 to the 5th power. And then 16, 4 and 4, 2 and 2. It's 2 to the 4th power, but it's a -4 because it's 1/16. 2 to the -4. 3x minus 2. Okay. The bases are now the same, so we just multiply the exponents. 5x equals -12x plus 8. Get x by itself. And then divide by 17. Get this fraction answer, 8/17. Once you get the Algebra 2 stuff out of the way, you know, usually it's a pretty easy Algebra 1 problem. But the Algebra 2 part, it's a little bit, you know, is where we kind of get stuck. Now, if you can get the bases the same, that's how you need to do it. What happens when we have a number that the bases can't be done that way with? That's where the logarithms come in. Okay, so still exponential equation, but we got 4 to the x equals 11. Something real basic. Not a whole lot going on there. My default thing to do is look at that and say, okay, 4 is actually 2 squared. But then I look on the other side and I got an 11. And what do we know about the number 11? It's prime, so it doesn't break down to be 2's. So when that's the case, we can't do it the same way to get the bases the same. That's where the logarithms come in, okay? And the way that you're going to use logarithms to solve these is whatever the base is that has the exponent with the variable, you're going to use that log base to get rid of it, okay? So on this side, it's a base 4. So if I use log base 4 of 4 to the x, I have to use log base 4 on the other side. So like log base 4 is like dividing both sides by a number. It's the same kind of idea. We're doing the same thing to both sides. On the left side, where the base and the log base are the same, they cancel each other out. All you're left with is x. And x is equal to the log base 4 of 11. That's the exact solution. Let's get the decimal approximation for that. So math, log base 4 of 11, 1.7297. Going 3 decimal places on all this stuff. So that 7 after the 9 makes the 9 go up to a 10, which makes the 2 go up to a 3. So that's 1.730. The log base and the base need to be the same. That's what cancels that out. Really, that's what operation is actually canceling out the bases when they're the same in the previous problems. But because they're the same base on each side, we can kind of just wave our hands and make it go away because it's the same. Let's look at one that's maybe a little bit more work to it. 7 to the 9x equals 15. Obviously, you cannot change a 15 into a 7 squared or 7 to the third or anything like that. That's not going to happen. So what log base do we use to get the exponent with the variable out of this? We use log base 7 of both sides. Whatever the base is that has the exponent with the variable in it, that's the base you want to use for your log. Because on that side, the log base 7 is going to cancel out the base of a 7 and leave us 9x. And I forgot to do log base 7 on that side. Equals log base 7 of 15. Is x by itself? No. How do you get x by itself? Divide by 9. Just like, log base 7 of 15, that's a number. It's not a very pretty number. It's a nice, ugly decimal. But it's just like if this were an 18 over here. You divide by 9 to get x by itself, just like any other equation. So x is equal to log base 7 of 15 divided by 9. We'll get the decimal approximation for that. So with my calculator, I'm doing math, log base 7 of 15. I'm just going to get that answer and then divide that answer by 9. 0.155. Not incredibly complex. They're not going to get really complex until they start putting the logs in there to begin with. And then it gets a little bit more interesting because there's more things you can do to the problem. Let's look at one more of these exponential equations, and then we'll get into logarithmic equations. 9 to the x plus 6 equals 41. Nice and simple. What's different about this one than the last two? It's got that plus 6. So if we get rid of that, then it's just like the last two we've done. How do we get rid of that? Yeah, subtract 6 from both sides, just like you would any other regular equation, but this is an exponential equation. So we have 9 to the x power is equal to 35. Now what do I do to get that x out of the exponent? Log base what? Log base 9 of 9 to the x, and then log base 9 of 35. What happens on the left side of this problem? The log and the base 9 cancel each other out, leaving us just x. The other side, log base 9 of 35, that's the exact answer. The decimal approximation to 3 decimal places. Math, log base 9 of 35. 1.618. And if you're you don't have your graphing calculator, you got a scientific, you can do that same log, remember, with the change of base formula by using log of 35 divided by log of 9 and get you the same answer. And that may be quicker for some of you to type it in that way instead of hitting the math button and then finding log base. Exponentials, get the part that has the variable in the exponent by itself, and you can use log with the same base to get rid of that stuff. All right, let's look at log equations or logarithmic equations. Logarithmic equations have the log in them already. So log of base 5 of 4x minus 7 equals log base 5 of x plus 5. This is the most basic of those types of equations. The log base 5, to get rid of an exponential, we used a log. To get rid of a log, we're going to use an exponentiation or an exponential. We're going to use, just like when we got rid of the 9 to the x, we got rid of the base of a 9. We used a log base 9. To get rid of a log base 5, what do we think we're going to use as a base to exponentiate with? What's the base of the log? 5. So that's the 5 that we're going to use to exponentiate. When you exponentiate, what you're doing is you're taking 5 as the base raised to the log base 5 of 4x minus 7. And then 5 is the base raised to the log base 5 of x plus 5. What happens here is when you exponentiate, this is what this is called is exponentiation. The little caret symbol there, that just means that's the exponent. Sometimes when I write it, it doesn't, sometimes it's hard to tell what's the exponent, what's not. So that just means you're exponentiating that side with a 5. You're exponentiating that side with a 5. The log base 5 and that 5 that's a base cancel each other out, just like they did when we were doing the exponential equations. So that these are gone. All I've got left is 4x minus 7 equals x plus 5. And then we solve that equation just like we would in chapter 3 of an Algebra 1 book. Just get x by itself. Subtract x. 3x minus 7. Add 7. 3x equals 12. Divide by 3. X equals 4. The only thing we have to worry about here, because these were logarithmic equations, and they had the log in it to begin with, is you cannot take the log of 0 or a negative number. So you've got to check your answers to make sure that they don't turn the original problem into having 0 or a negative number inside of the log. This one's not going to. 4 times 4 is 16. 16 minus 7 is a positive number. 4 plus 5 is a positive number. So that one's okay. If it does turn it into a negative, then you just throw that answer out. It's an extraneous solution, just like it was with the rational equations. So can't have a 0 or a negative inside of the log. So you got to check your answers with the logarithmic equations because they had the logs in them to begin with. All right, let's look at another one. Log base 4 this time of 5x minus 1 is equal to 3. So only one side has a log on this one. But getting rid of that log is exactly the same idea. What base should we exponentiate with here? 4, because it's a log base 4. So we make 4 the base of both sides. And I'm writing this extra step here. I would expect you to just kind of write that work in there. What happens to the log base 4 and this base 4? It cancels out because it's a log base 4 and a base of a 4. They cancel each other out, leaving us 5x minus 1. And then 4 to the third power. What happens over here? What is 4 to the third power? 64. It's a number, right? And now that's even easier. It's just a regular equation. Just get x by itself. Plus 1. 5x is equal to 65. Divide by 5. 13. Make sure that doesn't get a negative in the original equation. 5 times 13 is a big positive number. Minus 1 is going to stay positive. So that's okay. So that answer works out of that. Pretty easy. Log base 7. 3x minus 2 equals 2. What's going to get rid of that log? What do? I got to exponentiate with a what? 7. So I'm making 7 the base on both sides. That's kind of how I usually write that work instead of writing that extra step. That leaves us 49 on the right side. Log base and the base 7 cancel out over here, and it's just 3x minus 2 there. So these equations look really, impressive when you start them, but they're really not very difficult at all, actually. Divide by 3. X is 17. 17 times 3, 51 minus 2, 49. That works out great. So it's a positive number in there. So it's equal. Okay. Easy enough. All right. Let's throw in some of those properties that we talked about yesterday and how we could use those in equation solving. So the condensing is what you'll use the most in solving these equations. Something like log of 2x equals or plus, excuse me. That's unfortunate, wasn't it? We'll pick those up later. Log of x minus 5. You just got to laugh at it. It's okay. There's nothing you can do about it. Oh my gosh. All right. So with these, what's going on the left side? It's adding 2 logs together. Addition, when you're condensing, turns into multiplication. That's what the rules are. So we could condense this side down into log of 2x times x minus 5. And that's still equal to 2. Now there's only one log in the problem. And 1 is easier to get rid of than 2, right? What base is that log? 10, right? Anytime it's not written there, it's a 10. So if the base is 10, what do I use to exponentiate with? 10. 10. 10. That's easy work, right? 10 squared is 100. What happens on the left side? Cancels out. All I got is 2x, parentheses, x minus 5. But if I multiply those two together and multiply it out, what do I end up with? Yeah, 2x squared minus 10x. And if it's an x squared problem, didn't we do a whole chapter about quadratics? So we got to solve that quadratic. So it's 2x squared minus 10x equals 100. If we're going to solve that quadratic, what do we have to do? Get it equal to 0. Good, we remember. There's it equal to 0. 2x squared minus 10x minus 100. What could we do to simplify that? Everybody's divided by 2, right? Or divisible by 2. So divide everything by 2. X squared minus 5x minus 50 equals 0. Now, what are our options for solving this? Factoring or quadratic formula. I don't care which way you do it. It works the same. You get the same answers no matter which way. This one will factor. Not all of them will factor. So quadratic formula may be your default to go to just because you know it's going to work no matter what. I'm going to factor this one because I see the negative 50 and the negative 5. I know that that's negative 10. Or let's see. Yeah, negative 10, positive 5. So that's x minus 10, x plus 5. And then you set each factor equal to 0. And you get x equals 10, x equals negative 5. Remember, though, you've got to go back and make sure you don't end up with a log of a 0 or a negative. If I plug 10 into either of those logs in the original problem, that's 20, and then 10 minus 5 is positive 5. So 10 checks. But if I plug negative 5 in, 2 times negative 5 is a negative number inside of a log. So that doesn't work. So you throw that answer out. It's an extraneous solution. So just put an X through it like that to show that you got that answer, but it was a problem, so we threw it out of there. Okay. They're using that multiplication product property of logs. That one's used the most. It's the most common one that you'll see. Let's do one more here. Log base 4 of x plus 12 plus log base 4 of x equals 3. Can we condense the side that has the logs? What's it become? Go ahead and multiply it if you want to. X squared plus 12x. Save you a step later on because you're going to have to do that at some point anyway. Now what? Cancel out the log 4 with 4 as the base, an exponentiation with a 4. Those cancel. 4 to the third power. Done that one already today at 64. It's quadratic again. So that means we got to get it equal to what? Equal to 0. Subtract 64. Since I did factoring on the other one, do quadratic formula on this one. This one will factor too if you want to factor it. X equals negative b plus or minus 4 squared minus 4ac. All divided by 2 times a. Then simplify that. So that's negative 12 plus or minus 144 plus, because 4 times 64, is that 256? Is that what that is? Oh, my 64 is time tables. Yeah, actually I did. Got it right anyway. And 144 plus 256, 400 under that square root. So negative 12 plus or minus the square root of 400. What's the square root of 400? 20. So we got two answers. We got x equals negative 12 plus 20 divided by 2, negative 12 minus 20 divided by 2. We got to simplify those. Negative 12 plus 20 is 8. Divided by 2 is 4. Negative 12 minus 20 is negative 32. Divided by 2, negative 16. If I look back at my original problem, I know the negative 16 is going to get thrown out because it would put a negative in the logs. I'm going to throw it away. You're not always going to just throw away the negative. That's the most common one, but that doesn't mean you always throw it away. You really do have to check each set of answers to make sure on that, because sometimes, depending on what's inside of that log, you could keep a negative and throw away a positive, depending on what's there. So you just got to check them to make sure. All right, do a little practice with that. It's on page 519, 3 through 43. And we'll just do the odd ones. Some of them take a little while. Some of them are really fast problems. And some are not quite as quick, but that'll get you some good practice for that material. And then